Yeah, what I intend to do here is to probably summarize all the results that were presented this morning in a different way, in the form probably of what we could call recommendations for the industry. That is recommendation for the design and mostly for the design in the case of the study of impact on structures. Yeah, I'm just trying to get rid of this. Okay, sorry. So yeah, I will first say a few additional words on other results that we have developed during the project on the modeling of extreme sea states, and then I will come back on the results on the modeling of breaking waves and on the tools that were used during the project. This is mostly what's been presented by Fabien and Mathias. Then I will come back on what Jean-François just presented minutes ago, and both on the profile of breaking waves and also on the design sea states for slamming. But first of all, just some additional results on the comparison. First we made on different databases, sea state databases. These are Eincast databases. On the one hand, we have Omer, which was run using, which was built running WaveWatch 3, and on the other hand is Animoc, the database that was built by EDF LNHE using Tomahawk. So these two data sets cover the channel and the Bay of Biscay for periods of more than 20 years. So there are different configuration, of course, but it was really interesting to compare this. And here I will mostly present the results of the comparison in the case of the most energetic events and the storm events, actually. So we compared the two models, but we also compared each models with different buoys, which are available on the Candice network. So we selected 9 locations in the channel in the Bay of Biscay. So what we can say basically on the ability of these models to represent the energetic events is that they both are able to represent the storm events at this synoptic scale with a good timing. So the storms arrive at the good time at the location, and also in terms of duration. So it's already a good results. But what was observed is that there are other discrepancies in the distribution of the highest HS during these storms. One of the problems is that these differences also will vary with the location. The differences are not the same in the north of the Bay of Biscay and they are in the south of the Bay of Biscay, for instance. So it's really difficult to extrapolate some kind of a correction law to take all this into account. So even though the two models present some fairly comparable results at the synoptic scale, there are some important different regarding the ISHS, and this result is important because it will probably lower our confidence level in the extrapolated HS value that can be extrapolated for when considering n-year return values like 50 or 100-year return periods. So it's something that we can take into account. And also when we compare models, or when we use models, we have to make sure that the configurations that are used are adapted, have an adapted parameterization, which should be adapted to the forcing wind field that will be used as input. And so this is connected with the work that's been done and presented earlier by Fabien when we presented the case study for the stormy winter 2013-2014 that was, I would say, replayed with many configurations using WaveWatch 3, considering the two wind fields, the satellite blended winds and the Aero 5 hindcast, and also introducing various parameterization of the source terms. So we already presented the main results this morning, and the two first conclusion that we could have from this study was that when running WaveWatch 3 to build the hindcast database, especially for the characterization of design conditions, combining the Euro 5 wind fields with the test 500 parameterization probably provide the best alternative for the simulation of the sea states when considering the storms. And the second point was that if we want to reduce the uncertainties on the model's output, especially in coastal areas, we really have to have a special attention, give a special attention to the quality and accuracy of the elements that we use for the configuration, such as the bathymetry, the seabed roughness, but also the quality of the current fields and water levels, which are of real importance. All these parameters are of real importance in the definition of the configuration. Another point that can be presented here, an additional point, is the ability of the usual spectral formulation to represent stormy events or extra energetic events. So you know that all the information is comprehensively described by the directional spectrum, which can be decomposed in a frequency spectrum and a function that describes the directional distribution of the energy density. I will not talk much about the directional aspects here. I will focus on the spectral information. One of the most widely used formulation for the frequency spectrum is the Jones-Swap formulation, which requires information related to a wave height, or a significant wave height, a period, which is usually the peak period or the mean period, T02, and a specific parameter, which is the gamma parameter, which is the peak enhancement factor. And so the importance of this peak enhancement factor is shown here. So depending on the value of gamma, you can have a more or less wide distribution of the energy. For instance, for gamma equal to 1, you will have this blue distribution here with a wide bandwidth. And if you consider a larger value of gamma, then you will have a narrower spectrum with the energy centered closer to the peak frequency. This is important when considering the evolution of the wave distributions within the sea states, and especially when regarding braking and its effect on slamming and on loading on structures. So when you have a broader spectrum with a larger frequency content, you will have more, I would say, a less smooth free surface elevation with more waves and more variations, which is probably more prone to induce braking and impact or slamming afterwards. The other point is that this Jones-Swap formulation is based on the assumption that the sea state is unimodal, that is composed of just one single wave system, either wind, sea, or swell. But we know that most of the sea states are not unimodal. They can be the superimposition resulting from the superimposition of a wind, sea, and a swell, or a wind, sea, or even 2 or 3 swells, or different combinations of wave systems. So there are 2 questions when considering using Jones-Swap for the representation of storm sea states or energetic sea states. The first one is, are these storm sea states unimodal? And the second one is what is the best value of this peak enhancement factor that we should use to model our spectral distribution. So to study this, we've used the dataset, the hindcast provided by Omer. We've considered 10 locations in the channel in the Bay of Biscay. And as you may know, as part of the outputs from WaveWatch and available in the Omer hindcast, we have the information, especially on the significant wave height, the information of the partitioned sea states. That is, we have the significant wave height, access to the significant wave height of the wind, sea, and swells that compose the sea states. And this is this information that we've used here. So we first analyzed the distribution of these wind, sea, and swell significant wave height. And then afterwards, we studied the distribution of the gamma for storm spectra. So the first result, so based on the analysis, the statistical analysis of the distribution of significant wave height of, let's say, all unimodal sea states, unimodal wind seas, and unimodal swells, we can see that for the highest quantiles here, so the for the highest quantiles, we see that there is a large increase of the number of unimodal sea states. And so it's, for instance, for quantile 0.98, about 80% of the sea states are unimodal. This ranges between 70 and 90% when considering all the locations we've investigated in the study. And also, what we can see is that the HS for the quantile 98 for unimodal wind seas is higher than the HS for the same quantile for all unimodal sea states, so that we can conclude that extreme sea states are mainly unimodal, and the distribution of the higher significant wave height is larger for the unimodal wind seas. So this was the first result, and the second one is related to the assessment of the peak enhancement factor, the value of the peak enhancement factor. So you can find in the literature different formulation that will link the ratio between the mean period, the average period T02, and the peak period to this gamma factor. I'll give you here two of these formulations, but there are plenty more. The problem is in the distribution of the distribution of parameters we had. There was too large variability in the distribution of the ratios T02 over TP. So we didn't use this formulation, but we prefer to fit theoretical Jones-Webb spectra having the same HS and peak period than the Homer spectra that we had extracted. And for all the spectra, we try to adjust the theoretical Jones-Webb just by varying the value of the peak enhancement factor in the range between 1 and 7. The adjustment was made by minimizing the normalized RMSE that was assessed over the whole frequency range. And for this study, we only considered the most energetic systems or sea states, which were the sea states for HS larger than the HS associated with the 0.98 quantile. So altogether, we found for all the points a value that was comprised between 1.28 and 1.55, with an average of 1.4, and no correlation with other parameters or even with the location was identified. So based on all these results, we have three main recommendations or advice, probably we could call them like that. So sea states are associated with the extreme events are mainly unimodal wind seas, so that the statistical assessment of the parameters used for the characterization of extreme sea states for design studies should be established considering only unimodal wind sea events. That's the first point. When considering unimodal sea states, the Janswap formulation allows for a realistic representation of the frequency distribution of the energy density of extreme sea states. And for the channel in the Bay of Biscay area, which we have investigated here, an average value of 1.4 can be advised for this gamma factor. And the standard deviation associated with this is with this value is 0.25. So I haven't talked about the directionality and the directional aspect here, but we've also investigated the directional spreading for the same data set. And what we could see is that the this directional spreading is relatively limited in the case of extreme events, and an average value of 25 degrees with an associated 3 degrees standard deviation can be advised in terms of directional spreading. So this is for the climatologies for extremes. Now I just will browse through all the results that were presented this morning and just provide the recommendations or the conclusions that can be extracted from all this. So one part of the work in the DIME project was to also assess the capacity of the nonlinear models to simulate breaking waves. So two models were used: the fully nonlinear potential model developed by Greeley et al., and also the BOSS model, which is based on the Boussinesq approach, which was developed by Volker Wilbur. The first one, the fully nonlinear model is really an efficient tool to provide nonlinear wave properties up to the breaking limit. I mean, considering the limit of the overturning, and then to assess the loading on structure. One point is that it's not on open access, and it has a limitation that it stops once the overturning has taken place. So during the project, another model or an extension version was developed. So it's an alternative model. It's also a 2D model, but it takes into account irregular waves with a variable bathymetry. So, and also dissipation term was introduced in the model so that it allows to run simulations beyond overturning, so that we can consider a longer series of waves. So this model shows also a good ability to model the geometry of the wave, and especially of the front of the crest. But there's still some work to be done regarding the validation of the fluid kinematics at the crest when we consider using this model for slamming loading assessment, for instance. Regarding the BOSS models, so it's been presented. I mean, some results have been presented this morning by Matthias in his presentation on the Biarritz area. So what's interesting in this model is its ability to account for the kinematics and dynamics of 3D irregular sea states on domains which are relatively large. I mean, a few square kilometers. It's at least the size of an marine renewable energy plant. So it can be really interesting. And so it's been applied to 3 different sites and for 3 different tests. One in Esquibien in South Brittany, one at the La Jument Lighthouse that Jean-François showed you just earlier, and as I mentioned, the Biarritz location. And during the project, some developments were completed, improvement of both the numerical solver at the boundary and also the numerical scheme for the wave propagation. And also the new breaking criterion that was implemented in this model. So as Matthias showed, the BOSS has a good ability to model the energy gradient, and it seems that this ability is even better than the ability of the spectral models to really model the gradients of the energy over the given area. Probably the small problem with the use of the Bose model in the case of slamming loading is that it's probably the description of the vertical profile of the velocity up to the crest is probably not as accurate as in the other models. So that's still an interesting model. So the two conclusions here are so if an approximation of the design wave can be obtained by means of an harmonic wave train, a soliton, or a wave packet, that is a short wave group, then the fully nonlinear boundary element models allow for the identification of the necessary information for the estimation of the slamming forces. And when we are to take into account not just small wave packet, but irregular design C states, we can use the modified version of the model, which includes an attenuation term. This model has been developed and is now available, but in that case, it must be noted that the fluid velocity at the crest is probably underestimated, and there are some validation work still to be conducted here. Yeah, we now I'll just say a few words about the loading of breaking wave on a fixed wind turbine mast or a vertical turbine mast. So the results were presented by Jean-François just 10 minutes ago, so I will not get back into too much into the details. So you can see the importance. What is to be noted is the importance of the impact component of the loading as soon as the front of the crest is vertical and at least parallel to the structure itself. So this is really important, and it also shows that it's important in that case to consider an asymmetrical or asymmetric wave, which will correspond to the case of a plunging breaker rather than a symmetrical wave, sorry, which is probably more related to the breaking associated with a spilling breaker. So the two conclusions here are that the loading is predominantly of the impact type. When the wave shows a vertical crest front, it's then necessary for proper assessment of the extreme loading to provide an accurate statistical characterization of the front height parameter, together with the other parameters of relevance, which are the phase velocity and the crest height. And the second point is that models of regular symmetrical nonlinear waves can be used as long as the considered C states do not include waves having a vertical crest front. For other cases, considering a symmetrical wave provides a reasonable approximation of the loading, even for relatively asymmetrical waves. But again, as long as we don't have this vertical crest front. Yeah, probably the last aspect of this recommendation is related to the definition of the design C states for slamming. So the idea is, and the question we can raise here is how to characterize C states with a higher chance of slamming. So if you look at the literature, for instance, you have this reference by Paulson et al., in which they consider that the slamming loading for design can be considered as soon as the steepness, which is defined by the product of the average wavelength, average wave number, sorry, times the significant wave height, is as soon as this steepness is higher than 0.3. And if you look at the recommendation given by DNV regarding slamming on the cylinder, the chances for breaking are related to C states for which the significant wave height associated with a given return period, the breaking wave height is equal to 1.4 the significant wave height associated with a return period, the chosen return period, which could be 50 years or 25 years or 100 years. So there are two questions when we consider this kind of design criteria. So the first one is, are design slamming efforts necessarily correlated with the design C states when the design C states are defined as a function of the wave height or of a design significant wave height? This is not certain. And also, when we look at these approaches, it's clear that they don't take into account the type of braking, whether it is a spilling braking or plunging breaker. And the question here is, how could this be accounted for? So the approach that was preferred in the DIME project was to try to get in the direction of the response-based design approach. And the idea here is just to define the design C state not as a function of reference wave height, but defining the design C state as the C state, including the wave that would statistically induce the highest slamming load on the structure. So it's really based on the response of the structure. But to get this, there are two requirements. We need to have an assessment of the probability of occurrence of braking waves, together with the intensity of the loading associated of these extreme events. And so for the loading, we can use formulations such as the formulation provided by Godard, which was presented earlier by Jean-François for the impact on load, on cylinder. And regarding the parameterization for the braking probability, so these are the work presented earlier this morning by Fabien and the work by Stringari et al., which ended up in a new approach establishing a joint law between the fluid horizontal velocity at the crest and the phase velocity of the wave, and considering the Gaussian approach, which is related to linear waves. However, in spite of this assumption, it was possible to introduce a corrected theoretical braking criterion, which is alpha with a value of 0.25, and Fabien also showed that this value could be probably extended if we consider not just the limited spectral bandwidth limited to the energetic waves, but if we consider the whole distribution, we could extend this value up to 0.3. So the last recommendation associated with these results are so the definition of the design C state and design wave for impact loading must be based on a good knowledge of the C state statistics. That's the first point. And the second point is that it may result in a design C state or a design wave that differs from the usual design values, which are related to the highest waves classically. The second point is that the braking probability assessment can be based on works by Stringari et al. That were developed during the project. So with this value of the coefficient alpha. But it is necessary in order to close the problem to have a good knowledge of the statistics of the braking severity, the curling factor. So is it a spilling breaker or is it a plunging breaker? What is the occurrence of this kind of events, combined with the braking probability itself? And the last point is to be considered. It's not been discussed here, but it's important for the future and for future projects related to the outcomes of the DIME project. The dynamics of the floating systems relative to the impact wave should also be considered in order to improve the reliability of the slamming efforts assessment. So especially for the case of the floating wind turbines. So these are the main outcomes that we've tried to present in the form of recommendations to make them probably easier to handle. But as you could see, a lot of work has been done, and in that case, we often come with more questions at the end of the project than we had in the beginning. So there are still some challenges to respond to. And so, for instance, there is a clear necessity to improve the modeling capacity for breaking irregular waves in arbitrary depth. We also need to improve our modeling capacity for realistic extreme wave climatologies in coastal areas. So for bathymetries between the coastline and down to 200 meters water depth. There is a lot of effort to be done on the access to reliable observations of breaking waves in storms that are necessary to provide the necessary statistics and properties description for the validation of the models, and especially of the parameterization of these models. And yeah, there's a last important aspect, which is the definition of a breaking severity parameter, the so-called curling factor, and the associated statistics.